Today we're talking about Newton's method, a recursive numerical method for approximating a root of a function. Now let's define a couple of terms. First of all, as we discussed in an earlier video, a root of a function is a value of x that makes y equal 0, equivalent to the x-coordinate of an x-intercept. When I say it's a recursive method, that simply means that as we get more and more accurate, as we run the method over and over again, each succeeding root approximation is defined in terms of the previous one. And we'll see that when we write the formula for Newton's method. Okay, now let's take a look at how this is arrived at. Let's suppose that we have a function, y equals f of x. And we know that there's a root here. This x-coordinate we'll just label r for root. But it's not a root that we can find easily. Well, if we can determine, as we did earlier, you may remember when we were discussing Rolle's theorem, that we were able to use the intermediate value theorem to locate two integers between which we had a root. Well, if we can do that, if we can find an integer, and preferably an integer because they're easy to work with, that we know is close to the root, and I'll call that x sub 0. Imagine that this x sub 0 is very close to r, right? And x sub 0 that makes y close to 0. If we can do that, and we might do it by the intermediate value theorem, we might do it by simply drawing a graph, then what we can do from that point is at the point x sub 0, f of x sub 0, draw a tangent line. Now, if we have made a good choice, then that tangent line will cross the x-axis closer to the root than our first guess. I'll call this x-coordinate x sub 1. That will be a better approximation for the root than our first guess. Now, let's take a look at a very familiar equation. You may remember this one from elementary school or junior high. M equals, and we'll call it y1 minus y0 over x1 minus x sub 0. That is the difference in y's over the difference in x's. The simple equation for the slope. Now, let's use that as our template. The slope of this tangent line, since it is the line tangent to f at x sub 0, is f prime of x sub 0. Our y1, or f of x sub 1, is 0. Our y sub 0 is f of x sub 0. And x sub 1 and x sub 0 are exactly the same. If we take that equation, multiply through by this denominator, and then divide here, what we'll have is x sub 1 minus x sub 0 equals, now that 0 can be dropped, and we just have negative f of x sub 0 divided by f prime of x sub 0. Now, if we add to both sides x sub 0, we get x sub 1 equals x sub 0 minus f of x sub 0 divided by f prime of x x sub 0. We have just defined x sub 1 in terms of the previous guess, x sub 0. If we wanted to run this again, and now it would be very difficult for me to do this visually, we could, at the point x sub 1, f of x sub 1, draw another tangent line which would cross the x-axis even closer to the root. And if we did that and ran the same sort of calculation, we would find that x sub 2 equals x sub 1 minus f of x sub 1 divided by f prime of x sub 1. And in general, the recursive equation, the recursive definition for Newton's method is x sub n plus 1 equals x sub n minus f of x sub n divided by f prime of x sub n. You can run the calculations as many times as you need to satisfy the demands of the problem. You can run it until you have a certain number of decimal places that do not change, or you can run it if the problem just asks for x sub 1 or x sub 2, as many times as is necessary. But each time you run it, your degree of accuracy will improve. Now, so what do we see from this? This is just, I say just, but it's remarkably clever that we can take an old formula for just the slope of a line and use it with our derivative to approximate roots of functions. Now, back when we discussed the mean value theorem, and even before then when we were graphing, we saw that the intermediate value theorem could help us approximate roots of functions. And we're going to use it here to get a good first guess for a function, and then we're going to run Newton's method to get a better approximation. I'll leave that up here. And in fact, when we were doing our little lesson on the mean value theorem and Rolle's theorem, we used this function. F of x equals x cubed plus 3x plus 1. And then, at that point, we were just using Rolle's theorem to show that it had only one real root. But the first thing we did was we used the intermediate value theorem to kind of zero in on that root. And we saw, since this function is continuous, we were able to use that. We saw that f of negative 1 is negative 3, and that f of 0 is 1. So we knew that this function, being continuous on the interval negative 1 to 0, must have a root between there. There must be some value of x between negative 1 and 0 for which y equals 0. Well, now Newton's method is going to enable us to start zeroing in on that root. And we can get as close as we like by running it as many times as is necessary. I'll run it just once, maybe twice. But we'll see that Newton's method converges very quickly toward the root. Now, the root is irrational. We're not going to find it exactly, but we can get pretty darn close. Okay, so we need an x sub 0, a first guess. Let's remember that that's what we need for Newton's method. We need a first guess. We need the derivative, of course. And once we have the function, the derivative, and a first guess, we're off to the races. Well, since at x equals 0, y is closer to 0 than it is at x equals negative 1, all right? F of 0 is closer to 0 than f of negative 1 is. I'll use 0 as my first guess. I'll say x sub 0 is 0. Well then, x sub 1, following the template, is 0 minus f of 0, which I already know, divided by f prime of 0. Well, f prime of x equals 3x squared plus 3, which we saw in our previous lesson. So, f prime of 0 is 3. And our x sub 1 is negative 1/3. That is closer to the root than x sub 0. All right, let's do one more and then we'll wrap up. Let's do x sub 2. X sub 2 is x sub 1 minus f of x sub 1. Well, if we plug in negative 1/3, we get negative 1 over 27 plus negative 1 plus 1. So negative 1 over 27. Divided by f prime of negative 1/3. Negative 1/3 squared is 1/9. 3/9 is 1/3 plus 3 is 10/3. Well, what do we have here? We have negative 1/3 minus minus is plus. Well, 1 over 27, 10 over 3 is 90 over 27. So what do we have here is 1 over 90. One-third is 30 over 90, so negative 30 plus 1 is negative 29 over 90. And that is our x sub 2. That will be closer to the root than that. Now, notice something. I said that Newton's method converges very quickly, and it does. We went from 0 to 1/3. It doesn't seem like a big change, but compared to the change in the second one, we went from 30 over 90, or negative 30 over 90, to negative 29 over 90. A very small change. If we ran it again, which I will not because the arithmetic would be hellacious, we would have an even smaller change, perhaps something on the order of negative 291 over 900, but not even going to hazard that. That's as far as we'll go today.